Stanford University.
All right, I want to come to a new class of systems, which is a very interesting class of systems. They're usually called magnets, magnetic systems, but they may or may not have anything to do with genuine magnets. What is a magnet? A magnet is a collection of little magnets. Okay? And little magnets have the property that they point along, they tend to align themselves along magnetic field. But the important thing about them is that they're little systems which can point in any direction. Furthermore, whatever they are, whether they're little magnetic grains, or are they iron atoms, or something else, they are themselves little magnets, and it means they're like, what do you call those things that mariners use to figure out which way they're going? Compasses, yes. They're little compasses, except they can point in three-dimensional space. They have interactions between them, and the interactions tend to favor parallel neighbors. The interactions between them are fairly short range, which means that, roughly speaking, each magnet affects its nearest neighbors and tends to make it want to align in the same direction. That's the energy function will tend to be lowest when the magnets are aligned, biggest when they're anti-aligned. You can have the opposite, incidentally. You can have the situation where the little magnets the energy favors anti-alignment. Then it's not called a ferromagnet. A ferromagnet is a situation where they align. It's called an antiferromagnet, and it tends to make anti-alignment. But real magnets, ferromagnets, iron magnets, are systems where the little magnets tend to align each other. But they only align their nearest neighbors. Okay? Nevertheless, even though they only align their nearest neighbors, at sufficiently low temperature, it may be the case that the fluctuations are weak enough. At very high temperatures, they fluctuate like mad. Okay? At very, very low temperatures, only the lowest energy states are important. And the lowest energy states all have the magnets aligned along the same direction. Which direction? Well, any direction, but along the same direction. So a ferromagnet is a system certainly which at zero temperature, when there are no fluctuations, tends to align, and it aligns by the first one aligning the second one aligning the third one aligning the fourth one, and so forth. Or really, we're not thinking about a line of them, we may be thinking about a three-dimensional block of them, each one aligning its neighbors, and the whole thing in some collective way, all pointing in the same direction. As I said, at high temperatures, they tend to fluctuate wildly, and so it's not likely that at high temperatures, this phenomena of alignment will persist. Okay? All right, we make models. We make various kinds of models of magnets, mathematical models. The real thing, the real genuine thing, a bunch of interacting iron atoms, is much too hard to solve, if for no other reason that the interactions are not between just nearest neighbors. There's a tendency for the interaction to slop over to second nearest neighbors, third nearest neighbors, and this makes a nightmare of a mathematical system, too complicated to solve in detail, so we make simplified models. The first kind of simplified model is called the first kind of simplified model is even so simplified that it doesn't have any interaction between its neighbors. All right? The first kind of magnet we're going to study is not even really a magnet. It has no interaction between its neighbors. But the special simplifying feature of it is this is a magnet whose little individual magnets can only point in one or two of two directions, either up or down. It's called a Z2 magnet. Why Z2? Z2 is the group of two elements, up and down basically, but that's not important to us. It's called a Z2 magnet, and most studies, or most of the early studies of magnets, were about Z2 magnets. All right, so that means we're building our magnet out of little elements which have only two possible states. Either they're up or they're down. And we're making an array of them. We might study different kinds of models. We might study models in which it's a one-dimensional array. We might study two-dimensional arrays of them, and so forth and so on. We might even study very high-dimensional arrays, not because anybody can build a high-dimensional magnet, it's because the mathematics of high-dimensional magnets turns out to be especially simple, for reasons I'll tell you later. All right, so we have these systems which are composed of these elementary magnets, which are very simple. They either point up or they point down. And in the examples that we're ultimately going to want to study, there's an energy function which, let us say, favors neighbors being in the same direction. All right? So a high energy state would be neighboring magnets in opposite directions. A low energy state would be neighboring magnets in the same direction. And so at zero temperature, which will pick out the lowest energy state, there are only two of them, either all magnets pointing up or all magnets pointing down, all the little elementary magnets pointing up or all pointing down. I'll assume for the moment that the system is symmetric with respect to up and down. If it's symmetric with respect to up and down, then the energy function, whatever it is, between two neighboring magnets, will be one thing if the two are parallel, in other words, the same energy if they're both up or they're both down, and a higher energy if one is up and one is down, or one is down and one is up. That's a simple system that we can try to study. An array of them, one-dimensional array, two-dimensional array, three-dimensional array. In fact, we could just study two atoms like this. We'll call them spins. What they have to do with spins, nothing is spinning. It's just a name for them, spins. And the spin is either up or down, and the energy favors having them parallel. So at zero temperature, they will all line up, either up or down. Which is it going to be? Is it going to be up or is it going to be down? The answer is both are low energy states, so we can say they're, well, technically we would say the ground state is degenerate. Two possible equal energy ground states, or lowest energy states. But that means whether it's up or down is going to depend on minute effects, such as, for example, a tiny, tiny stray magnetic field. A tiny, tiny stray, by a tiny, tiny stray magnetic field, I mean some almost infinitesimally small magnetic field, extremely small, which might even be too small to measure, but still might favor one direction or the other. There are so many of these little magnets, and they're all in this infinitesimally small magnetic field, and so they all line up in that direction. If we changed this infinitesimally small magnetic field from up to down, all the spins would want to be down. No matter how small that magnetic field is, the ground state will either be all up or all down. And if we imagine the limit in which that background magnetic field gets smaller and smaller and smaller, the magnetization means the tendency for all the spins to be up or all the spins to be down. It doesn't go away. It just stays there until the external magnetic field reverses sign, and then they might all simultaneously reverse sign. This is called spontaneous symmetry breaking. The system has a symmetry. What is the symmetry? You take all the spins and you flip them. You turn all ups to downs. If you turn all ups to downs, the energy stays exactly the same, ignoring this little stray field. All ups have, they don't have to all be up. Whatever the configuration is, it might be one up and one down. If you turn them both over, you get one down and one up, same energy. So this system has a symmetry. The symmetry being, let's give these degrees of freedom a name. Let's call them sigma. Sigma of I, the ith spin. And it's either plus or minus 1. +1 if it's up, -1 if it's down. All right, that's our system, a collection of these simple degrees of freedom. The symmetry, here's the symmetry. All sigmas, sigma of I for all I goes to minus sigma sub I. All spins flip. Everything about the system is exactly the same. But if you put on the tiniest magnetic field, it will tend to line it up in that direction. And that direction is not symmetric. I mean, it's all up. So that's called spontaneous symmetry breaking. Spontaneous means that it doesn't go away as you shrink the bias. We can think of the bias being the tiny magnetic field which might bias it in one direction. We let that magnetic field external magnetic field get smaller and smaller and smaller, and eventually we take it away altogether and the spins are left all up. If we started with the magnetic field in the opposite direction, the external magnetic field in the opposite direction, and then gradually removed it, all the spins would be down. So there would be two possibilities, but either of them would break the symmetry. Breaking the symmetry means that the configuration would not have the symmetry of up goes to down, but would be biased in one direction or another. That's the phenomenon we want to study. Now, another reason for studying it, magnets are kind of interesting, of course. They're lovely little toys to play with. But another reason for studying these kinds of systems is because you can model an enormous number of statistical mechanical systems as magnets. Let me give you an example. A gas, a fluid. A fluid is a correct collection of molecules. Okay? But I can try to represent that collection of molecules in the following way. Break up the container that contains them into cells where the cells are about as big as a molecule. Let's suppose these molecules have hard cores and that we can't stick them on top of each other. Then if the cells are about as big as a molecule, then we can't get two particles or two molecules into a box. And so either a box is empty or it has a molecule in it. Again, two possible states for each box. It's either got a molecule or it don't got a molecule. We could call having a molecule up. We could call not having a molecule down. And then this system of molecules moving around, let's put molecules in various boxes. This would correspond to a spin up, a spin down, 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 up over here, down everywhere else. And we map the mathematical problem of the gas of molecules into the mathematical problem of the magnet. That's a very, very fruitful avenue of exploration, and it has been a fruitful avenue of explanation. And for example, let's pursue it. Let's pursue it before we actually get into the mathematics of it. Let's think about it a little bit. What would correspond to the configuration in which all the molecules were up? Full. We absolutely chock full this system. We make the system extremely dense. What corresponds to all the spins being down? Empty. So the configuration with all molecules up is the high density limit. The configuration with all spins down, that's the low density limit, or the vacuum to be specific. But let's just call it the low density limit. Okay? What corresponds to a configuration where there are equal numbers of ups and downs? For the magnet, we would call that unmagnetized. We would call it unmagnetized because on the average, every spin is equally likely to be up and down. So it's perhaps the situation where there's enough fluctuation to make on the average every spin be zero. What would that correspond to this system here? Half full. It would correspond to the density half full. Okay? Now, let's think about what happens to the magnet when we have a little bit of a magnetic field. We have a little bit of a magnetic field, and let's suppose it's some finite temperature. It's at some finite temperature, and we put a little magnetic field which tends to make it point down. Okay. All right, if it's at some finite temperature, there will be some fluctuation. All the molecules will not literally point down. There will be some fluctuation, but on the average, they'll point in the direction of the magnetic field, but maybe with only a weak bias. As the temperature goes up, of course, the bias goes away and they tend to fluctuate more. So at low temperatures, but not zero temperatures, what we'll find is that on the average, the magnets will be down, but not with a full 100% magnetization. And now we start changing the magnetic field a little bit, and we vary it. Gets smaller and smaller and smaller, the external magnetic field, and finally becomes zero, but then we turn it on with epsilon amount of it, tiny amount, in the opposite direction. What happens? Well, if the magnet had spontaneous magnetization, in other words, if this phenomena of spontaneous symmetry breaking was active, then there will be a sudden jump in the magnetization, a sudden jump from more spins down to more spins up. What does that mean for the fluid? Well, the density. The density makes a sharp jump. As we vary some parameter, let's not worry about now exactly what parameter to vary, but as we vary some parameter, whatever the natural analog of the magnetic field is, we'll find it's the chemical potential, in fact. But as we vary some quantity, there's a sudden change from a biased situation where more spins are down. What does that mean about the density? Less than half. To a jump where the density is more than a half. What do we call that? A phase transition. And it's a phase transition from a less dense configuration, we might give a name to that. We might call it a gas. To a more dense configuration, we might give another name to that, a liquid. Okay? So just as an example, many, many systems can be modeled as these simple magnetic systems. We call them magnetic systems, but they stand for a lot of different kinds of systems. And that's why they're so useful. They're useful for magnets, but they're also useful for fluids. The magnetic transition, where sudden spontaneous magnetization happens, that's also the gas-liquid phase transition. So that's why we study them. And we don't just study them because they're magnets, which are interesting in their own right, but because they are a broad brush description of many, many different kinds of statistical mechanical systems. I've given you two, the magnet on the one hand and what's called the lattice gas on the other hand. The lattice gas is incidentally not always a gas. It can be a liquid or a gas depending on which phase it's in. Before we actually study such systems, let's talk about them broadly first. Let's make a plot. And on this plot, let's plot temperature on the horizontal axis. Low temperature, everything fluctuates a minimum amount. At zero temperature, it just picks out the ground state. At high temperatures, it fluctuates maximally. And on the vertical axis, let's imagine an external magnetic field. Let's see, we can put the whole thing in a magnetic field. How can I represent the magnetic field? By an arrow with a different color. Incidentally, we're restricting ourselves to magnetic fields which are either up or down, not pointing sideways. So we have an external magnetic field. Let's call it H, little h. Why H? I don't know. It's a traditional name for the magnetic field in these spin systems. H. Let's start at zero temperature. no fluctuations. What happens if h is pointing up? Well, h will point up, it will bias all of these spins, and it will say they're not fluctuating, so push them into their ground state, but there are two ground states. The low temperature will make sure they're in their ground state, but there are two ground states, all up or all down. Which one is going to be favored? Well, that will depend on the direction of this magnetic field. This magnetic field adds a little bit of energy, which is different for an up and a down spin. And so if they're all up, that might be the lowest energy. So when h is positive, let's call it the average magnetization, the averages of the spins, it will be magnetized upward. I don't know, let's just say the average of sigma is greater than 0 in this region, magnetized up, and in this region where the magnetic field is down, oh boy, that was my bag, sigma is less than 0. Now it may or may not be, but generally it is, that if the temperature is low enough, this state of affairs persists right up to almost zero magnetic field. And then across here, there's a jump. A jump, sigma less than 0 here, and sigma greater than 0 here. So there's a phase transition across here. Let's just put a bold line there of some kind. And if we go across here, in other words, if we fix the temperature, low temperature, and vary the external magnetic field, there will be a jump of the magnetization across here. That jump in magnetization, as I said, corresponds to a jump in the density of the analog fluid here. Okay. Now, this situation typically persists, as we'll see, out to some finite temperature. And then beyond that temperature, the fluctuations in the system are so strong that it destroys this tendency for the spins to align themselves when the external magnetic field goes to 0. They'll be aligned down here only because of the presence of the external magnetic field. They'll be aligned up here because of the external magnetic field. But right on the axis here, the net magnetization, the net tendency to be up or down, the net expectation value of sigma will be 0 along here. And so this jump will disappear, and everything will be completely consistent, completely smooth as you go across here. Again, this here corresponds to the liquid phase, high density. This corresponds to the gas phase, low density. If you fix the temperature, you have a jump. Now I'm going to tell you what this H is. This H is actually the chemical potential. Corresponds to the chemical potential. It's the thing that you use to vary the density. Of course it's the thing that you use to vary the density. The more you vary the external magnetic field, the more you'll bias it to either greater or lesser density. So H is the chemical potential in the analog. And if you want to vary the density, you vary H, but it varies discontinuously at some point, and that's the gas-liquid phase transition. So you can go to gas, from gas to liquid, by crossing this boundary and having a sudden jump in the density. That's just the usual thing that happens when there's a transition from vapor, which is very low density, to liquid water, which is higher density. But you can also do something else. You can go around here and go from gas to liquid without passing through any transition at all, without passing through any discontinuity at all. That's called going around the critical point. And some of you who are familiar with the properties of the gas-liquid phase transition know that you can go from water to steam without passing through a sudden abrupt change by going around the critical point. So that corresponds to going around the critical point. I'm pointing these things out just to show you that this, these lattice systems have a lot of physics in them, a lot of familiar physics and sometimes some unfamiliar physics. Okay, we're going to study these lattice systems a little bit. Yeah.
In the case where you're talking about the magnetic system,
Yeah.
you change that external magnetic field a little bit. Let's say you're at very low temperature.
Yeah.
Is there kind of a hysteresis effect when you're right at zero field?
Is there a hysteresis? You mean if you go around in a loop?
Well, no, not if you go around a loop,
Right.
but if you just keep the temperature down below the critical point there. Do you have to, because you've got some interactions between all these spins, do you have to put a little extra field on there?
You're asking whether there's a metastable phase. You're asking whether you can have metastability, the analog of what happens if you were to lower the temperature of steam below the temperature of the transition, and you're very, very careful. Can you keep it steam? I think that's what you're asking. Yeah, I think that's the issue of metastability. Metastability. Can you vary this H and go down to here, keeping all the spins upward? And the answer is typically yes, but if you sit there, it's not true equilibrium. It's not true equilibrium. If you take a system, let's take these little magnets, all right? Now, we've ignored the question of what causes the magnets to change their direction. All we've done is talk about their orientation. We haven't talked about the kinetic energies which might cause them to actually move. But let's imagine that there was something in the system which caused them to move. All right. So you start with a magnetic field downward. They point downward. And then you very, very carefully increase the magnetic field. And you will come to a point, if you're very, very careful with a magnet, where the magnet will be pointing in the wrong direction relative to the field. That's called a metastable situation. But if you sit there and you wait there long enough, sooner or later, a fluctuation will happen. A fluctuation will happen. One of the spins will realize, or a group of them, a small group of them, will realize that they can find lower energy configuration by flipping themselves over. And once they flip themselves over, that thing starts spreading out and creates a bubble of spins which all then right themselves and get themselves oriented in the right direction. So it's called metastability. It's not really equilibrium. It's out of equilibrium, but it can take a long, long time for equilibrium to set in. And that's the root of metastability. Yes, that can happen. And it's closely connected to the phenomena of metastability in the gas-liquid system, where you can cool or otherwise change the parameters of a gas-liquid phase transition, gas-liquid system, where you might be able to, one way or another, very carefully change the liquid or change the parameters so that you move into what should be the gas region, but nevertheless the system not budge and stay liquid. But if you sit there and wait a little bit, sooner or later, a little bubble of gas will form, and then the bubble of gas will take over the whole system.
Is that supercooling or superheating?
Yeah.
Question?
Yeah, it's connected with hysteresis, yeah.
The question is, in the case of, you said this is Z2, but in the case of these magnets, when they flip, a normal magnet would radiate energy where we're ignoring that aspect.
Yeah, we're not asking about the kinetics of the system, right. But I'll tell you, all right, but you can ask what really you can ask what really does happen for magnets. Now, real magnets are, of course, not these Z2 magnets. They are, right. So you could imagine trying to orient the magnets with a magnetic field, change the magnetic field to get into an unstable situation, but then typically what will happen is after a while they'll start to slosh around what they'll radiate away is spin waves. Spin waves are sort of waves of wiggly magnetization. But there are no spin waves for this situation because they're either all locked up, well, everyone is either up or down and nowhere's in between. So, they could flip, for example, by emitting sound waves. They could flip by emitting light waves, but that would be unusual for a real magnet. A real magnet doesn't flip itself over. when a compass changes direction, it usually doesn't emit a lightning bolt. I mean, it might emit a little tiny bit of sound into the, not much. Well, very, even that would be hard since the, yeah, very, right, very, very low frequency radio waves, right. More likely just some sound waves or something which are easier to, but, or some pressure waves, or who knows, I don't know. Anyway, this is what we want to study. I'm not going to study these things in as much mathematical detail as I do in the notes that I've distributed to you. I'm trying to decide, yeah, I think what I'll do is give you an illustration of the phenomenon of spontaneous magnetization in an approximation which is called the mean field approximation. This is one of the many approximations. I'll tell you the various approximations that we apply to these kind of magnetic systems. There are approximations which are called low temperature expansions, where you begin with the system at 0 temperature and you expand your way in powers of something involving the temperature. Right? There are high temperature expansions where you start the system at the infinite temperature where it fluctuates like mad, and then you expand about 1 over the temperature. High temperature expansions. They're not very hard and they're not very difficult, but it's not where we're going to go. Then there's another kind of method called renormalization group. That's a method that I will maybe tell you a little bit about as we go along, but not tonight. And the other method is called mean field approximation. And mean field approximation is a nice physically intuitive picture of how this phenomena of spontaneous magnetization takes place. That's what I want to do tonight, is show you the mean field description of this. And mean here doesn't mean nasty, it doesn't mean cheap, it means average. Okay, mean field approximation. Now, what we're going to imagine is that we have a lattice. And it might be a 3-dimensional lattice, which might be the case we're really interested in, or it might be a 2-dimensional lattice. I don't want to deal with the 1-dimensional lattice for reasons that perhaps we'll discuss. But let's start with either a 2-dimensional lattice that I can draw on the blackboard, or a 3-dimensional lattice, or better yet, a D like David, a D-dimensional lattice. And the reason I say a D-dimensional lattice is because this approximation works best when D is very large, for reasons that I'll explain. The reason is very simple. The reason has to do with the fact that the higher the dimension, the more neighbors that any given atom has, or any given site has. In 1 dimension, each site only has 2 neighbors. Okay? In 1,000 dimensions, how many neighbors does 1,000? 2,000 neighbors. Yeah, 2,000 neighbors in 1,000 dimensions. In 2 dimensions, each one has 4 neighbors. In 3 dimensions, 2 more, 6 neighbors. So 2D neighbors. Now, the reason it's good to have a lot of neighbors is because you can average over the neighbors. You can do an average over the neighbors and say this molecule at the center sees the effect of a large number of neighbors, and it doesn't matter much if one neighbor is a little bit different. You can average over the neighbors. You can use the laws of large numbers, so to speak, statistics, to average over the properties of the nearest neighbors. So it's as if we in this room formed a lattice, which you do form sitting there in your chairs, although it's a rather irregular lattice. And you're interested in the properties of your neighbors and what your neighbors are doing to you. Well, if there are enough neighbors, you can average over them and say the effect of my nearest neighbors on me is to have this particular effect, which is the average over large numbers of neighbors. If there's only one or two neighbors, then averaging over them might be a less effective thing to do. And this is true for this kind of system. So the mean field approximation becomes accurate, infinitely accurate or perfectly accurate in the limit of large numbers of dimensions. But we're not really interested in the limit of large number of dimensions. Well, it turns out numerically that 2 is a little bit large, and 3 is large already. In other words, mean field approximation works pretty well for 3 dimensions. But more important than whether it works numerically well is it gives you a picture of what happens that leads to this magnetization. All right, now, we're going to invent now an energy function. An energy function which is the energy function, well, for this system of atoms. Each one is either up or down. Let's represent an up by a dot and a down by a cross. The energy only depends on the orientation configuration of nearest neighbors. All right? The energy is low when they're parallel and high when they're anti-parallel. So here's an expression which does that. Let's take the energy to just be, let's call it sigma of I, sigma of j, but now I and j represent neighboring points on the lattice. As you range over I and j, I really only want you to imagine that you're ranging over nearest neighbors. Nearest neighbors on the lattice. And let's put a minus sign in here. Now, if sigma I and sigma j are the same, in other words, if they're both +1 or -1, then sigma I, sigma j is 1, and the energy is negative. Negative is low. All right, so this favors or lowers the energy when they're parallel. What about when they're anti-parallel? When they're anti-parallel, then the energy is +1. And so there's 2 units of energy stored in every bond if the bond is a broken bond. Now, what do I mean by a broken bond? Let's say an unbroken bond is a bond where the spins are parallel. Here's an unbroken bond. A bond means a nearest neighbor link of the lattice. Here's another bond which is unbroken. The spins are parallel at the 2 ends of it. A broken bond would be one like this one over here, where the spins are anti-parallel. Broken bonds cost you energy. How much energy? Each broken bond costs you 2 units of energy. So energetically, it's profitable to keep the number of broken bonds to a minimum. But on the other hand, as you raise the temperature, because there are so many possible configurations with broken bonds, raising the temperature will tend to create a population of broken bonds there. All right, so that's the picture. Now, we're going to do an interesting approximation which really captures some of the interesting physics. Let's focus on one molecule. Let's focus on this molecule right over here. I don't know whether it's up or down, so I haven't biased it. But let's focus on this one over here. And let's write the expression for its energy. Its energy, let's call this sigma 0. That's sigma 0. Right at the center, the spin that I focus in on is called sigma 0. It's +1 or -1. And it interacts with all of its nearest neighbors. So its energy, the energy of sigma 0, let's call it little e. Little e represents the energy of this spin in the background of all of its neighbors. And what is it? It's minus sigma 0 times the sum of all the spins of all the nearest neighbors. Sum over nearest neighbors of the nearest neighbor spins. I'm not going to try to make too much. That's enough terminology, enough indexology. Okay. Let's suppose that the spins have an average value. Okay? An average value that the system is magnetized. Let's suppose, it may not be. We'll find out if it's not. In other words, let's suppose that on the average, each spin has the same value as each other spin, and let's suppose on the average of any spin is called S. Now, S is a number between -1 and 1. The average of a thing which can only be 1 or -1 must lie between 1 and -1. So whatever S is, the average spin, it's between 1 and -1. S is the thing which is called the mean field, the average value of all of the spins. And now, each one of these spins sees around it a whole bunch of spins. If the dimensionality of the system is high enough, it sees loads and loads of spins around it. And so it has some average energy in the background. This one has an energy in the background of all of these. Right? And what is its energy? It's just equal to minus sigma naught times, now on the average, each one of these sigmas is equal to S. So that's N, or sorry, that's twice D times S. Why twice D? That's because that's the number of nearest neighbors. Twice D is the number of nearest neighbors. So I've replaced each one of these by its average. There are 2D of them. And so that particular spin right at the center is experiencing a bias or a effective energy which is proportional to that spin with a minus sign, whatever it is. Now, S can either be positive or negative. We don't know offhand whether S is positive or negative. They may have a tendency, maybe 0. Maybe on the average, S is equal to 0. Then this would not be magnetized. It's magnetized if S is not 0. And S can either be positive, or it can be negative, or it can be 0. And that's what we want to find out. But let's assume that there's some finite value of S. Now that we know the energy of this particular spin in the background of all the others, let's just do some statistical mechanics for this one spin in the background of all the others. We're freezing all the others. Well, we're not freezing them, we're freezing their average value. And we're going to think of sigma naught as a little system all by itself at temperature T. And let's see what we can learn about it. Let me not call it sigma naught anymore. Let me just call it sigma. It's just the one spin that I'm focused on now. And it has an energy. It's energy. E stands for energy now, which is equal, as I wrote over there, twice the dimensionality of space. S, that's not ds, that's just d times s. It doesn't stand for the differential of S, times sigma. And let's write the partition function and the statistical. Yes. Let's write the statistical mechanics for that spin. The probability function for it is e to the minus beta times its energy. But its energy is just this. So that gives us a plus 2ds times sigma. That's the Boltzmann weighting factor. Next, let's calculate the partition function. Okay? The partition function is the sum over the two possible configurations of the spin. We're just doing the probability distribution for the single spin in the field of all the others. And so let's just write that this is the sum over sigma. Sigma equals plus or minus 1. And so what do we get? We get that the partition function is just equal to e to the twice beta ds plus e to the minus 2 beta ds. I've just added the two configurations, and this is the partition function for this very simple system in the field of all the others. Okay, that's Z. How do I calculate the average energy of this spin? Well, we first have to take a logarithm. Right. All right. This is also twice the hyperbolic cosine of 2 beta ds. Okay, that's that step. Let's take its logarithm. Log of z is equal to, first of all, log of 2 plus log of cosh of 2 beta ds. What about the minus the log of z is, of course, just this. Now, what is the energy? The energy is the derivative of minus log z with respect to beta. That's the thermodynamic identity or the statistical mechanics identity we've used over and over. So the energy, but not the energy of the whole system now, just the energy of this one spin. I'll just call it, what shall we call it? Well, basically it's the average value of little e here. The average value of this little spin is, it's the average value of the energy of this one spin. What is it given by? It's given by the derivative of minus log z. Let's see, so what is that? That's minus 1 over hyperbolic cosine of 2 beta ds. And then we have to differentiate the hyperbolic cosine with respect to beta. That gives us hyperbolic sine 2 beta ds. And then we have to differentiate what's in here with respect to beta, so that gives us another factor of 2 d times s. Okay. This is the important factor over here. It has another name. It's minus the hyperbolic tangent of 2 beta ds. Okay. That's the answer for the average energy. But what about the average value of the spin itself? What about the average value of sigma itself? Well, the energy of sigma is sigma minus sigma times 2d times s. If I wanted the average of sigma, I would just take the average of the energy and divide it by 2ds. Spin and energy just differ by a factor of minus 2ds. So if I simply divide the average energy by 2ds, I will find the average value of the spin. What is that? Here's 2d, here is, well, let's see. I think I left out something. Yeah, here it is, 2ds times 2ds. If we just cancel this 2ds, then we have the average value of the spin. I think I also want to cancel the minus sign. That's the average value of that spin by doing statistical mechanics on that spin. Incidentally, if you plot hyperbolic tangent, the function hyperbolic tangent, if we plot beta this way and hyperbolic tangent vertically, it looks something like this. It goes to 1 at this end and minus 1 at this end. What does this correspond to? The maximum value that tangent takes on is 1. The minimum value that it takes on is minus 1. This just corresponds to the statement that that the maximum value the average of the spin can take on is 1 and minus 1. This end out here, or both ends actually, are low temperature when beta goes to 0. So when beta goes to 0, sorry, when beta goes to infinity, When beta goes to infinity, that's low temperature. And don't ask me about this side over here. I'm going to come to that side over here. It's a little weird, isn't it? What does that mean? Negative temperature. Weird, huh? Yeah, okay. We'll come to negative temperature, but let's focus. But this is the average value of the spin as a function of beta. The spin is a function of beta. All right. Yeah.
You could relabel, it's interesting, you could relabel the x-axis S and you get the same shape.
Yeah. 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 We're going to do that in a minute. Right. Good. All right. So this is the average of the spin. But now, this only makes sense if the average value of the spin over here is the same as all of the other spins. After all, we're assuming that every spin is like every other spin, and so we have a consistency requirement. The consistency requirement is just that this average value of the spin here be equal to the average value of the spin, S. And this becomes an equation for, if you like, the magnetization, the magnitude of the magnetization, S itself. S is the average of the spin, it's the amount of magnetization, and this becomes a self-consistency equation. Let's just go back. What did we do? We said, look, in the limit of a large number of nearest neighbors, we can average over the nearest neighbors. And just think of an average behavior of the nearest neighbors. Assume that the nearest neighbors on the average have a spin S, then the energy of our friend at the center here will be minus sigma times 2ds. And now knowing that, let's use the statistical mechanics to calculate the average value of S. And once we've done it, consistency requires that it just be the same as the input S in the first place. So here we are. What do we have to do? We have to satisfy this equation. On the left, we have S. Let's draw the graph of just S. You're right, we can put S over here. Tangent 2 beta S we'll put S on the horizontal axis. What is the significance in terms of this graph of changing beta, let's say D is fixed. D is 3 dimensions now. What's the significance of changing beta? It changes the slope at the origin here. Right, that's all. It just spreads the curve out or shrinks it together. What happens when beta is very small? It spreads it out like this. So this is beta small. Well, that's not the axis. This just stands for small beta. What about large beta? Supposing beta is enormously large. Yeah. That means it looks almost like this. But this curve and that curve are related to each other. They're just shrinking along one axis. Just squeezing it along. Well, I didn't quite do it right. The height of this should have been the same as the height of this. This corresponds to 1 unit over here. This is 1 unit over here. All right, so I didn't draw it well, but that's the picture. Now let's draw S as a function of S. On the left-hand side, we have S. On the right-hand side, we have this tangent. We want to set them equal. That just means superimposing on this diagram a straight line. At the point where they intersect, S will be equal to tangent 2 beta S. All right, what about here? Where do they intersect? They only intersect at the origin. That's the only place where they intersect, is at the origin. And the implication of that is there's only one solution of the equation, and that one solution of the equation is magnetization equal to 0. Okay? That's what happens at small beta, and small beta means high temperature. Now you start lowering the temperature, and as you lower the temperature, this curve migrates to this curve, and what happens over here? Now there are actually three solutions. There are three solutions. And to calculate which solution is actually the right solution, you have to calculate the entropy and see which one corresponds to the highest entropy. All right? Turns out these two have the same entropy, and this one is some higher entropy configuration, which actually corresponds to some kind of metastable configuration. Here is the solution. Another way you can do it is to imagine that there is this little weak magnetic field. If there was a very tiny small magnetic field, it would bias you to one of these two solutions, depending on which way. Incidentally, these two solutions correspond to the two possibilities for the magnetization, either on the average up or the average down. They correspond to S equals something positive or something negative. All right? If you were to bias the system with a little bit of external magnetic field and really work it out carefully, you would find out that only these two solutions persist. That's all that's there, and that's what happens. So what happens now? You start changing the temperature, and at some point, the slope of the tangent function here gets to be equal to the slope of the straight line here. And after that, there's the intersection that corresponds to the magnetized phase. Where does that happen? That happens when the slope of this function becomes equal to 1. That's just when twice beta d is equal to 1. When twice beta d is equal to 1, then the tangent curve here becomes equal in slope to the straight line. And beyond that, it has this new intersection over here and over here. That's where the magnetization happens. So, in effect, we have found the temperature, the beta, at which this phenomena first happens. It happens, let's see, what is it? It's when beta is bigger. We have spontaneous magnetization. This is spontaneous magnetization. Yeah. When, let's see, beta, which is 1 over the temperature, times 2d is equal to 1, or temperature equals twice the dimension of space. All right. The temperature equal to twice the dimension of space, whatever, and space would be 3 for a 3-dimensional system, so at a temperature of 6 units, and 6 units in what unit? Well, we would need to put some units in here by putting a constant into this formula over here. This is not dimensionally consistent. Sigma is either plus or minus 1, and energy has units of energy. We have to throw in another constant over here to give it units. That other constant would appear over here. Yeah, let's call that constant J. I always call that constant J. Then it would appear over here and has units of energy. Okay. The main point is, you see what the pattern is, that as you vary the temperature from high temperature to low temperature, or from low temperature to high temperature, let's start at the low temperature situation. At the very lowest temperatures, this is a sharp jump here. And what does it say? It says the magnetization is either +1 or -1. So at temperature equal to 0, it's just temperature equal to 0, T, you jump as you go across here from magnetization -1 to +1. Two possible solutions. And then as you increase the temperature, let's see what happens as you increase the temperature. If you increase the temperature to a high enough point, beyond to a temperature higher than this, there's no more solution other than the solution at 0. Okay? So that means as you increase the temperature, at some point, At some point, the spontaneous magnetization disappears. The spontaneous symmetry breaking disappears, and there's only the solution with sigma equal to 0. No magnetization over here. But up to that point, there is magnetization. So we have exactly the situation that I described when we began. And we have a jump in the magnetization that's associated with a jump from here to here. If we bias the system a little bit with a little bit of external magnetic field, one of the two of these will be the lower energy configuration, and it will dominate the physics. All right, so that's the phenomena of spontaneous magnetization. One other point, notice what happens to the intersection over here as you go to this point over here. As you go to this point over here, let's track it. So let's start with, okay, so here's very low temperature. And now we raise the temperature. This curve starts to move over to this, like that. This point moves down. And as we lower the temperature, we eventually come to this first point where the crossover is. And the crossover, the crossing of the two curves migrates continuously to the origin here. And the meaning of that is that there's magnetization all along here. In other words, there's non-zero average of the spin, but as you move toward this point here, the average magnetization goes away and disappears at that point, and then it's gone. Okay, what's this point called? Anybody know? Critical point, Curie point, yeah, critical point. T critical, right. What would it mean for a fluid? What does it mean for the gas-liquid phase transition? It means that as you move to the critical point, the density difference between the gas and the liquid goes to 0. Over here, more spins down. Over here, more spins up. There's a gap, a separation in the value of the density as you jump from here to here. But as you go above the critical point, or right to the critical point, right at that point, the liquid and the gas density are exactly the same. And then beyond that, there is no liquid-gas distinction. Okay, temperature is higher than the critical temperature. So that's the mean field approximation to the critical point of the Ising magnet. I didn't tell you, this is called the Ising magnetic system, Ising, I-S-I-N-G. Ising didn't invent it. He solved the one-dimensional version of it, which takes about a quarter of a line of paper. It's very trivial. His thesis advisor asked him to study it as an example of phase transitions, and he did. And he discovered that there's no phase transition in one dimension. Now, that doesn't seem consistent with this. When d equals 1, there still seems to be the same phenomena. But the point is, in one dimension, it's a poor approximation. There aren't enough nearest neighbors to average over. He solved it correctly and found there was no phase transition. And from that, he concluded that there are no phase transitions, period. He was quite wrong. But he did get his name to be the most famous name in statistical mechanics because his thesis advisor happened to give him the right problem. Anyway, the Ising model, these are called the Ising models, and in dimensions higher than 1, the mean field approximation is a good approximation and says that there's a critical point, magnetization up to that critical point, no magnetization after that, and the magnetization smoothly goes to 0 as you go to the critical point. All right, so that's this took shorter than I expected it to, so let's have some questions. And I don't want to start a new topic now, yeah. What was J? Oh, J is just a constant. Let's just go back to where it came from. I wrote that the energy of the system was minus sigma I, sigma j. Yeah. Now, sigma is a dimensionless variable. It takes on magnitude 1 and -1, so it's dimensionless. So this is not dimensionally consistent if I wanted to restore some dimensions. So what I would do is I would put a constant here with units of an energy. All right? J, I suppose J for joule, I don't know. And then it would reappear over here, because it always multiplies the dimensionality of space, right?
Could you go to the logic again for S equals the tangent hyperbolic 2 beta ds?
Well, what we find when we isolate this one spin and think of it in the background of all the others is that its average in the background because of thermal fluctuations will be tangent 2 beta ds. All right? Now that's just one spin out of all these others. What we've assumed is that there's an average spin for every spin on the lattice, which are all the same. Every spin is like every other spin. And we've assumed that the average spin is equal to S. That was our starting point. We replaced all the nearest neighbors by S. But then this is only consistent if when we calculate the average of any one of the spins, it's equal to the average that we assumed in the beginning. So we assumed an average value for all the other spins. We then calculated the expectation or the average value of the one spin that we treated honestly. All the others we just treated as averageable, as something we can average. This one spin we treated honestly in the background of the others, and we found out that at a given temperature it has an average which is equal to this. The only consistency, the only way this can be consistent, since we assumed that the average of a spin is equal to, we called it S, is for these two to be equal. So it's just the consistency of the original assumption that the average of the spin is equal to S. And this is incidentally, this method of mean field is a common method in physics where when you have a lot of degrees of freedom, you focus on one of them and you assume the average value for all the others. Then, using the average value for all the others, you study the dynamics of the one additional degree of freedom, and then in the end, when you've calculated the averages for that one additional degree of freedom, set them equal to the averages that you assumed for all the others. That's called the mean field approximation. And as I said, it's a widely used approximation, and it is most effective in situations where any one degree of freedom is in direct contact with a large number of others that you can average over. In terms of the dimensionality of space, it means that what's called the coordination number, the number of nearest neighbors, is large. The way you can get the number of nearest neighbors to be large, there's only one way, and that's to let the dimension of the lattice get large. So then you have the perfect right to ask, okay, you've convinced us about something in the limit of very large numbers of dimensions. We might believe it for 1,000 dimensions. We might even believe it for 100 dimensions. We might even believe it for 10 dimensions. But where should we start to disbelieve it? And the answer is you should start, it depends of course on the degree of accuracy you want. But if you want something like 20% accuracy, or you just want 20% accuracy for the critical temperature, and okay, D equals 3 is fine. It's a good approximation for D equals 3. It's a so-so approximation for D equals 2. I'll tell you the exact numbers. If you calculate the critical temperature, here's the critical temperature. Where was it? Setting J equal to 1. Here it is. Setting J equal to 1. All right. For 2 dimensions, T is equal to 4 in some appropriate units. The correct answer, if I remember, is about 2.7. So it's not good and it's not horrible. For 3 dimensions, I don't remember the exact numbers. Of course, I can do 2 times 3. That I'm pretty good at. It's 6. But I don't remember the exact. Let's see. the critical temperature is always lower. The real critical temperature is always lower than the mean field approximation. So I don't remember the exact numbers, but it's, you know, it's within 20% or 15% of the right answer. And by d equals, well, we're really not interested in 4 dimensions, 5 dimensions, and 6 dimensions. It's reasonably accurate for d equals 3. Gives you the right general picture, and is even quantitatively within about 15%. I can't remember the exact number. D equals 1, it completely breaks down. It completely breaks down. It says T equals 2D. The actual answer is T equals 0. The critical temperature is 0. In other words, you never even really get started. At temperature 0, it's true that there's a magnetized phase, either all up or all down, but the smallest amount of temperature will disrupt it. Incidentally, I can tell you the physical reason for that. There's an interesting, simple physical reason why you can't have this kind of spontaneous order in one dimension, and why you can have it in higher dimensions. Let's think about all of the configurations of the one-dimensional theory. Let's start with all spins up. So what we're starting with is a little bit of bias, which makes all the spins be up. And now let's look at all the configurations that we can build on top of that. What can we do? We can start flipping spins down. What happens? How much energy is stored in one spin flipped down? Can anybody figure that out? 4. Each broken bond costs you 2 units of energy. You have to go from -1 to +1. So each broken bond costs you 2 units of energy. This costs 4 units of energy. How about flipping 2 spins down? Are they next to each other? Very good. Are they next to each other or are they not? What if they're not next to each other? Then the answer is 8. But what if they are next to each other? 4 again. What if they're 3 apart? 4. There's an infinite number of configurations which cost you no more in energy than just one flipped spin. Whole big blocks of them, flipping them over, cost you no more energy than one of them. That's the main reason why the magnetized phase is unstable when you increase the temperature a little bit. There's just a lot of configurations which cost the minimum amount of excess energy. What happens in higher dimensions? Let's take higher dimensions. Let's take 2 dimensions. Again, start with all spins up. And now flip one of them over. How much energy does that cost? 8 units of energy. How about 2 units? How about 2 spins flipped? 16 if they're far from each other, but how much if they're next to each other? 12. Let's see which are the broken bonds. Here's a broken bond. Let's just color green the broken bonds. 1, 2, 3, 4, 5, 6. This is not a broken bond over here. So that's 6 times 2 is 12 units of energy. That's more energy than just one flipped spin. Okay? Here's the way you can count. Draw a perimeter around the islands of flipped spins. Imagine flipping islands of spins. Imagine islands or groups of them adjacent, flipped. And draw a boundary around them like that. And then count how many bonds this boundary passes through. How many? Well, it's proportional to, but the main thing is, there's no way to flip a lot of spins without costing a lot of energy. The cheapest you can do, if you want to flip 100 spins, the cheapest in energy is to have them form a compact group of them Well, probably not a square. Probably, yeah, maybe a square. Maybe a square. And then the number of broken bonds is proportional to the surface, well, is proportional to the boundary. Right? It's in one dimension, boundary is just 2 points. And so when you flip whole blocks of spins, it just breaks 2 bonds. But in higher dimensions, trying to flip large numbers of spins becomes costly because you'll have to break a lot of bonds. The number of bonds does not grow as fast as the number of spins, but it does get bigger and bigger. And that's why there's this stability to the higher dimensions, to the magnetization in higher dimensions than there is in 2 dimensions. Because every island of spins is surrounded by a bunch of neighbors which are holding it fixed, and to flip large numbers of them becomes costly, whereas in 2 dimensions, big blocks of spins are only held in place by 2 bonds. Not a very stable situation. The technical mathematics of it we can postpone to another time. But that's the intuitive physics of what's going on. So in fact, you could conclude from this that there's no gas-liquid phase transition in 1 dimension, and there isn't. There is a gas-liquid phase transition in 2 dimensions. Now, who's interested in 1 dimension and 2 dimension? Well, it turns out that there are lots of systems in solid-state mechanics, solid-state physics, and in condensed matter physics, which are approximately, in some sense, either 1-dimensional or 2-dimensional systems. Systems of long chains of molecules, or planes, or flat planes of molecules. And these lower dimensional systems do have a real utility, a real application. But as I said, in 1 dimension and 2 dimension, 1 dimension there is no gas, liquid, or magnetic phase transition. In 2 dimensions and higher there is. And in very high dimensions, mean field approximation becomes extremely accurate.
So this is only for lattice systems?
Well, the tools that I showed you were for lattice systems. There's more general systems that we could study. Incidentally, it's kind of fun to try to do a better approximation than the simple mean field approximation. And here's the game. You again pretend that all the spins are equal to S. But then you unfreeze 2 of them, not just 1 of them, you unfreeze 2 of them, and you study the statistical mechanics of pairs of them. 2 of them free to fluctuate, 2 adjacent ones free to fluctuate, and you calculate in the background of all the others the average value of any one spin of either of the 2 of these. Okay? You do that, and then you set the average value of either one, they'll be the same, equal to the background spin, and you get a better approximation. You get a better approximation because you've allowed one nearest neighbor to each one of them to fluctuate, and you get a better approximation. It's an improvement. You can go further. You can study 3 spins at a time in the background of all the others. You get an even better approximation, okay? Eventually, you can study all the spins in the background of no spins, and you get the exact answer. But it is fun. I once worked out the 2-spin case in the background of the others, and you do get a numerically quite a good answer for the 3-dimensional case. Yeah.
A moment ago, you said negative temperature is interesting.
Oh, well, yeah, let's come to negative temperature the next time. Yeah.
How did they figure out the
We didn't have to think of this as negative temperature. We could just think of it as negative S.
Okay.
Right. That was the right way to think about it, not as negative. Yeah.
How did they get the exact number? You said they had an exact number.
This is an exactly solvable, okay, all right. Comparing high temperature expansions and low temperature expansions and discovering that they are very close, well, something called lattice duality, which you will find written up in the notes that I distributed on the internet, the lattice duality argument. And it's a very elegant, beautiful mathematical observation about these systems, but I didn't want to do it here. But this 2-dimensional system, the 2-dimensional Ising model, is exactly solvable. It has enough symmetry and enough special structure that it is exactly solvable.
Is there a name for the 2 free element solution?
For this, No, you mean the mean field with 2 spins unfrozen? Is that what you're asking?
Yes.
Not that I know of.
There's something called the Bethe approximation.
To which?
Is it Bethe approximation?
Beta, Hans Beta. No, that's got nothing to do with this. That is one-dimensional systems, but not the Ising model. The Ising model is too simple. I mean, if you apply the Beta approximation, it would be like hitting a peanut with a sledgehammer. No, it's for one-dimensional systems, and it's for one-dimensional systems with more complicated kinds of interactions, which cause them to what are called Heisenberg magnets, not this Ising magnet. He first worked out the Beta method of solution is applicable to something called Heisenberg ferromagnets, not to the Ising ferromagnets. So, yeah.
You described this in terms of gas-liquid phase transition. Is it equally applicable to liquid-solid phase?
No. The liquid-solid phase transition is a transition from a homogeneous configuration to one which is crystallized, where all the molecules line up in a definite lattice. And it's a sharp transition where the system goes from a disordered liquid phase to a sharply ordered lattice configuration. Now, the problem with this system, and the reason that it can't exhibit that kind of phase transition, because it's already biased by having its own lattice, and there's no sharp transition between a lattice symmetry and no lattice symmetry, because it's already got its built-in lattice structure. So no, there is no notion of a solid-liquid phase transition for this system.
Okay. And then a related question from gas-liquid. Does that mean if you put a liquid through a very small capillary, you can't tell whether it's a liquid or a gas? Because that's effectively one.
I would have said if you put it above the phase, above the critical point, you can't tell if it's a liquid or a gas. No, I think okay. I think you're right. If you take a small enough sample, you can't tell if it's a liquid or a gas. Phase transitions are things that happen in the limit of infinite number of particles. Phase transitions never happen for finite number of degrees of freedom. For finite number of degrees of freedom, there are never sharp phase transitions or sharp discontinuities. And the way you can see that is you can look at the structure of the partition function. The structure of the partition function, when you have finite number of degrees of freedom, the partition function is a finite sum over finitely many particles, and if it's a spin system like that, over finitely many configurations of e to the minus beta times the energy. Each contribution from every single state is an analytic smooth function of beta. And when you add up a finite number of analytic or smooth functions, you get a smooth function. Phase transitions are singularities, places of discontinuity of some sort as a function of temperature. So for a finite number of degrees of freedom, you never get phase transitions. There are never, the partition function is always completely analytic. It takes an infinite number of degrees of freedom. Basically, these sums have to be infinite sums, and if the spins only take on values of 1 and minus 1, well, you'll have to have an infinite number of spins before this can add up to something singular. So, right, so in fact, you cannot tell the difference between a gas and a liquid at any temperature, except maybe 0 temperature, but let's forget that. At any temperature, you can't tell the difference between a gas and a liquid or any of these things by looking at small samples. It takes large samples and then even if the sample is very, very large, its magnetization is not infinitely stable unless it's infinitely big. It just requires an infinite background to hold the whole thing together. So there's two different ways, in two different situations where you can't tell the difference between a gas and a liquid. One of them is just studying small samples. Okay? The other is when you have a critical point like this and you go around the critical point. There's no sharp place where you go from gas to liquid. The properties sort of smoothly go from one to the other. Yeah.
I wonder if you could remind us exactly how the thermodynamics of this particle is. We've got it going back to like the baths. Each particle is thought of as one of the baths which is in equilibrium.
Well, I wouldn't call the rest of these heat baths. I would just call it the mean field. The reason I wouldn't call it heat bath.
A mean field bath, which still has to, in order to apply the Boltzmann statistic to it, we have to exchange energy with it. It's with the surroundings in some way, don't we?
Yeah.
So what does that mean exactly?
Okay, it means that there are other little terms in the energy which cause, when you put them into the equations of motion of the system, cause transfer of energy back and forth. Now, we haven't talked about this, but I will discuss it for a moment now. If you have a system whose energy, let's use the language of quantum spins now, okay? Language of quantum spins. So sigma then has three components, sigma 1, sigma 2, and sigma 3. The sigma that we've been talking about here could be the z component, the third component of the spin. And there would be a term in the energy which would just be proportional to sigma 3 of one particle times sigma 3 of another particle, with a minus sign. All right. From the point of view of the mechanics, or the quantum mechanics of this system, sigma 3 will never change with time. There's nothing in, think of this as a Hamiltonian. There's nothing in this Hamiltonian which doesn't commute with sigma 3. In fact, the only things in the Hamiltonian are sigma 3. There's nothing which doesn't commute. Now, I'll remind you, because I know you've studied quantum mechanics at least a little bit, that the time derivative of something, do you remember the formula for the time derivative of a quantity? The commutator with the Hamiltonian. Do you remember that? Okay. So the commutator of I times the commutator, is it A with H or H with A? I don't remember, but that's good enough. There's nothing in this system here which does not commute with sigma 3. So what this means is this system, if you were to lay it down and lay down a given configuration, it would never change. It's completely static. There's nothing in it which would allow it to change. Of course, that also means it would never come to thermal equilibrium. You need a little bit of interaction of a different kind, something which doesn't commute with these sigmas. So you could add something like a tiny, tiny little number, epsilon, times the first component of sigma 1, sigma I, times first component, sigma 1 of J, and maybe another one with sigma 2 and so forth. You'd have to add something in that doesn't commute with the sigma 3s to give it time dependence. As it is, it doesn't have any time dependence, but you always imagine in the back of your mind that there are tiny little interactions between things which can cause them to change. This system as it stands doesn't have anything in it which would tell you how things change with time. You know what it's like? It's like having an expression for the energy in classical mechanics which only had potential energy, no kinetic energy. If a system didn't have any kinetic energy, it wouldn't move. It would have energy depending on its position, but it wouldn't have anything, it would have nothing in its dynamics which would cause it to move from point to point. So you can think of this here, the term that we included, as the potential energy of this lattice of molecules, ignoring the kinetic energy which causes things to change.
But somehow or other that additional kinetic energy is going to allow these things to get into some sort of equilibrium.
Yeah, it allows them to get into equilibrium, it allows them to change with time, to approaching equilibrium, but interestingly enough, it has no effect whatever on the phase diagram, on the nature of phase transitions. That's all determined by potential energy. and surprisingly. Kinetic energy doesn't play any role in these phase transitions. The system finds the configuration, well, the potential kinetic energy doesn't play any role. Kinetic energy doesn't play any role.
So that in the end, we find the thing up with the probability 2 beta ds and down with the
Yeah, but you must always imagine, as you say, you must always imagine there's a little more to the system which must be very weak in order that the energetics is mostly dominated by the things you've kept, but you must always imagine there's a little more which brings the system to thermal equilibrium.
But I guess what I'm wondering about is, are there some systems that you might think you could model this way, but you'd go wrong if you did?
I can't think of any offhand.
In other words, we're talking quite a general class of...
Well, if we try to use this to describe how a fluid flows out of a little hole in a container, and how the fluid goes from inside the container to outside the container, it would never do that. We could never study the approach to thermal equilibrium or the approach to anything. So we would completely fail to study anything that involves the time dependence of the system. All we can study is the equilibrium properties. But I think you're asking whether there are systems whose equilibrium properties wouldn't be correctly described this way. Well, I'm sure we can invent them. Yes, we can certainly invent them. Any mixing in the Hamiltonian between kinetic and potential terms, between position and momentum will... the reason we get away with this is because the energy consists of two pieces. One which is completely potential and only depends on the positions, and the other which is completely kinetic and only depends on the momenta. And remember, the partition function is an integral over positions and momenta. The potential energy doesn't make, the integrations over the momenta don't care about the potential energies, and they just factor off completely. They just factor off, and they're exactly the same as if the molecules weren't interacting with each other. The potential terms are the things which know about the interaction between molecules. The other factor doesn't. And so all of the properties of the gas which are interesting with respect to the phase transitions and so forth have to do with potential energy. Crystallization has nothing to do with kinetic energy. All it has to do with is finding the configurations of molecules which form crystal lattices, and that's got entirely to do with potential energy. Minimizing a certain combination of potential energy and entropy.
Yeah, a couple of weeks ago you were describing coarse and fine-grained entropy, and I seem to remember that you said in coarse-grained entropy that the Louisville theorem is violated.
No, I didn't say the Liouville theorem is never violated. No, it's a theorem. Theorems can't be violated. Theorems are either wrong or right. The theorems are never violated.
That's why. Weren't you saying that when the little strands get really skinny and you have a delta P, delta X that's wider than that, that doesn't violate the...
No, because the Liouville theorem is not about coarse graining. It's just not about coarse graining. It's about the fine-grained system. It's just not a theorem about the coarse-grained entropy. It's strictly a theorem about the fine-grained entropy. So how could coarse graining violate the theorem about fine-grained entropy?
Let's try to understand the relation,
Okay. But you might have imagined a wrong Liouville theorem which says that the fine-grained entropy doesn't change, that the volume of, the coarse-grained entropy doesn't change. That would not be a theorem. It's violated, but it wouldn't be a theorem, and nobody ever thought it would be a theorem. Right. Okay. But so if I announce the new theorem, this is the Schmierville theorem or the Louisville theorem. The Louisville theorem. The Louisville slugger who invented the Louisville theorem said that the volume in phase and coarse-grained phase space is constant with time. Well, that would have been violated, yeah.
Real quickly, can you explain what happens when in the phase space as the thing turns into the area turns into a very wavy kind of cotton candy kind of thing,
Right.
and then you have we're talking about coarse grain.
Well, okay, so I say take that cotton candy and look at the volume actually occupied by the candy. It's very tiny, very tiny. But on the other hand, if you were to take every little spot along the fibers and put on that spot a little ball about that big, of course they would crash into each other, but if they crash into each other, just let them overlap. And to take the volume that would be carved out by this coarse-grained version of the cotton candy, where every point is blurred over a certain size, it would fill up the area that the pink cloud of, right. So there are two different descriptions of volume. One of them is the coarse-grained volume, where I don't know what the right word is. Coarse-grained is the word, but where you let each little piece of the cotton be replaced by a little sphere, and the spheres, eventually the cotton will get so close together that the little spheres will begin to overlap, and those little spheres will fill up the volume that visually you would see in this cloud of cotton candy. Much bigger volume. So as the cotton candy is spun out, it starts as a little glob of sugar that big, and if you coarse grain a little blob of sugar that big, it's that big, not much bigger. And now it starts to spread out its tentacles in all directions and create this cloud of cotton candy. But now you replace each point along that fibrous structure with a little sphere, it'll occupy a volume which is much bigger. So as you spin out the cotton candy, it seems to grow, although the actual volume of sugar is exactly the same. That's what happens. Cotton candy, that's a good example. Right, that's a very good example. I will use it next time.
For more, please visit us at stanford.edu.